wearables and robotics. That health of all, I think, is known for the touch sensors, and we are really excited to hear your talk today on perceiving, understanding, and interacting through touch. Thank you very much, Roberto.
Thank you very much for having me here virtually today. And today I'll basically be talking about perceiving, understanding, and interacting through touch. And it's going to be a little bit of a brief journey over the work that we've been doing over the last 15 years. So the first thing that I would like to sort of share with you is really the importance of touch into our everyday life as humans. Touch is the primary sense that we use whenever we interact with the world. Every time that we want to grasp an object, every time that we want to search in the dark, these are tasks where touch play a really, really important role because it enables us to understand what are the geometry of what we're touching. It enables us to understand what are the contact forces, weight, slippage of all of the interactions that we have while we manipulate the world around us. And although other senses like vision might give us some cue about the contact and what's happening when we interact with the environment, the primary informations are actually really coming from touch. And very importantly, touch does not only give us information about, for example, the contact that we are creating, but also information about where this contact is happening. And some of the examples of the importance of touch are due to the work of Roland Johansson and colleagues at the University of Umeå. And what they did in their work was to show that very simple tasks like lighting a match, in the moment when we anesthetize the sense of touch to the human while keeping their motor control capability, suddenly this very task, the same task becomes much, much harder. And in this case, it takes 3-4 times longer to be able to light a match. Now, what is very fascinating about this demonstration here is actually the fact that eventually the human is able to learn on the fly how to compensate for the lack of touch. But as a default policy, the human is trying to use touch, and in the moment when there is no sensory information, is basically having problem to compensate. Now, in the context of robotics, about 6 months ago, there was a very interesting article from Rodney Brooks, a very famous robotician. And in this article, he basically was arguing what is wrong, in his opinion, about humanoids today, and dexterity was one of the main problems. And he's basically citing, saying these words: humanoid robot will need a sense of touch and a level of touch sensing that no one has yet built in the lab in order for them to do tasks like the one above, which is of the same order of difficulty that millions of workers do all day, every day. Now, this sentence was very interesting to me because I completely agree with Rodney Brooks on the fact that humans will need, humanoid robots and more generally robots will need sense of touch. At the same time, what I greatly disagree with Rodney Brooks is the fact that no one has yet built in the lab the right level of touch sensing. And so throughout the rest of the talk, I'll basically be trying to show you the fact that we actually do already have this level of touch sensing necessary. And my hope is really that in the next few years, more and more of these touch sensing capabilities will sort of go out in the real world and be used also commercially. So let me start from a slightly historical perspective of how I like to think about touch. So in the 1890s, with the introduction for the first time at scale of telephones, what was possible was for the first time in human history to be able to easily communicate over long distances. You could just take a phone, you could call on the other side of the world, and you could transfer your voice as a sensing modality from one side to the planet to the other. And this enabled very rapid sort of evolution in our societies, because suddenly communication was instantaneous. It was possible to talk to other people, and with all the benefits sort of associated with having this type of capability in our societies. At the same time, as a scientist, the fact that we were able to record, transfer, and replay back audio also enabled the creation of a new field of computational science dedicated to making sense of audio as a sensing modality. In its more modern incarnation, things like natural language processing, where you can talk to a computer, the computer is able to understand what you're saying, process it, and answer back. And a similar process happened in the 1990s with the first introduction at scale of CMOS sensor. And suddenly, we are now able to take digital photos of the world around us. We're able to digitize them, put them on internet, and share them with our friend. Or we are able in real time to just call our grandmother and talk to her, see her. And similarly, for what happened with audio, also in this case, we had huge impact on our society about this availability of being able to suddenly transfer videos and images from one side of the planet to the other. But also we had the creation of a field of computational science dedicated to making sense of images as a sensing modality. Arguably, the most successful field of machine learning is computer vision, and computer vision has been 60 years in the making as a field which has grown very large, very successful in being able to understand images, processing images and videos. And the way that I like to think about touch is that we are now on the verge of being able, for the first time in history, of mass manufacture cheap, reliable tactile sensor that enable us to digitize touch with the same type of accuracy and resolution that we have in our fingers. And this will, in my opinion, results not only in groundbreaking changes in our society, because it will enable us to do things that we can barely even consider now, but it will also enable us to create, as a scientist, a new field of computational science dedicated to understanding touch as a sensing modality. And I will be discussing a little bit more about this new field of computational science that we like to call touch processing in a few slides. Now, when I think about touch, I also like to think about it as a perceptual system. And so what it means is that touch sensing is not only the hardware, is not only the algorithm, but effectively is together these three aspects of hardware, of what do we sense from the world, the computational infrastructure, so how do we process this information in real time, and finally the algorithm themselves, how do we process these informations, what type of representation do we extract. And based on this concept, the sort of pillars that we've been developing over the last few years in this grand vision of touch sensing consists of hardware, of touch processing, of simulators, which are really important, and benchmark and dataset. And in addition, we've been working quite a lot also in applications and community building efforts. So in terms of hardware, if we look at the human, what we can see is that our skin is actually not a single sensor that is sort of equally distributed everywhere, but it's actually composed of many different sensors into a single modality. In particular, the type of receptors that we have in the skin are usually divided into mechanoreceptors, which are receptive to mechanical stimulation, thermoreceptors, so temperature, nociceptors, which are responsible for pain, and finally proprioceptors and chemoreceptors, which are responsible for physical internal sort of informations and chemical informations, respectively. Now, the most interesting sensor are probably the mechanoreceptors. And also in this case, when we think about mechanical sensations like the shape of the object that we are touching, this is actually divided on its own into several mechanoreceptors. The most sort of studied ones are the Merkel cells, the Meissner corpuscles, the Pacinian corpuscles, and Ruffini corpuscles. There is also a fifth one, which is called Krause end bulb, which it's still a little bit unclear from the literature what's exactly the role, but we know that it's basically a nerve ending and it's probably connected with temperature, but we are not quite sure. Now, what is interesting about these four different main mechanoreceptors is the fact that they have very different properties. Some of them are shallow, so they're closer to the epidermis. Other ones are deeper. Some of them are slowly adapting, so SA1 and SA2. Other ones are rapidly adapting. And what it means is, in practice, that they capture and they fire, they get stimulated from different aspects. So, for example, the slowly adapting ones will be better typically at a spatial resolution, while rapidly adapting ones will be more perceptive to vibrations. And when it comes to tactile sensor and robotics, over the years, there have been many different type of technologies that people have been studying and attempting to use in the real world. But very sadly, the large majority of sensors that exist in the literature have always remained at the state of prototypes. So one PhD student spent years to bring the prototype, and at the end, they write a paper, and then this prototype take dust for the rest of eternity in the university. And commercially, there are really only a handful of products that are available or that can be that are open source and can be reproduced. Now, when it comes to the factors that we typically care about in tactile sensors, there are several. One of the important factors is, of course, availability. So how easily can I get access to these sensors? How expensive is going to be the sensor? Because especially if you think about full humanoid robots, you basically need to have meters and meters of sensors distributed. In the case of the hand, of course, you can be you can have less surface to cover. The form factor is also very important. So do I want to have something that is extended? Do I want to have something that is very small and miniaturized? How much also depth can I use? Capabilities is probably the most important one. So what exactly are we measuring here, and at which resolution? Are we going to measure normal forces? Are we also capable of measuring shear forces? Are we measuring deformations? How fast can we measure these things, and also at which resolution? And finally, reliability. Unlike vision, which is a kind of a passive sense, in tactile sensing, every time that we are going to interact with an object, we are going to have wear and tear because we are going to physically enter in contact, and we are going to some level, slowly destroy the interface that we are connecting with the world. And as a humans, we have this amazing skin that regrows and regenerate over time. But we currently don't have technologies that can do this for tactile sensors. And so we need to be very mindful of what type of mechanical reliability we have in our sensor and how long can they last. Now, the type of technology that we've been mainly using over the last few years is so-called vision-based tactile sensors. The idea of vision-based tactile sensors is very simple and consists of having an elastomer, which is, you can think of it as a piece of silicon. And on this piece of silicon, we are going to project structured light, typically colored, but there are also other alternatives. And after that, we are going to have a camera that look at this at the elastomer and is going to record changes in the deformation in the shape of this elastomer as changes in color Q. And this type of technology has many advantages, but the main advantage, or one of the principal one, is the fact that we are able to leverage the fact that the transducer is a camera, and cameras is something that we can buy very cheaply because of market mass producer, which is easily available, very cheap, very mass produced, is very convenient. At the same time, the fact that this transducer never physically enter in contact with the rest of the world also means that in principle we can just keep using the same transducer even when there is wear and tear of the sensor. We will see, for example, by replacing the silicon. Finally, we don't have any moving part, and also in terms of wire management, we can have a relatively small number of wires compared to other type of technologies like capacitive or resistive that instead will need hundreds or thousands or millions of wires. Now, funnily enough, the vision-based tactile sensor technology is actually a very old technology. The first paper that produced this type of technology was actually in the 60s, and this technology was then reinvented in the 80s independently from multiple groups, and then again in 2000. And finally, Ted Adelson from MIT is one of the person that helped to repopularize this technology around 2009. And our first contribution to vision-based tactile sensor has been the design and open sourcing of the DIGIT sensor. DIGIT was the first mass manufacturable miniaturized vision-based tactile sensor. And the idea was that we wanted to have a sensor which is maybe not the best sensor we can build, but at the same time that is cheap, it's affordable, it's easy to use. You can just plug it in as a USB device, and it's very robust. So you can basically use it for multiple type of manipulation and robotic applications. And finally, it was entirely open source, so it was very easy for people to be able to reproduce it. You can also notice in this diagram how there is a screw in the front of the sensor, and this screw was basically for being able to replace the silicon. So unlike previous sensor, we invented this concept of cartridge for the sensor, where whenever the sensor gets ruined by contact with external object, we can just unscrew a single screw, remove the top part of the sensor, and replace it with a new piece of silicon in less than 30 seconds. Now, if we look at the type of output, sensory output that we get out of this sensor DIGIT, what we get are these images, very colorful, where it's possible to see the very fine geometry of the object that we are touching, down to a resolution of about 20 to 50 micron, depending on the silicon that you're using. And so, for example, on the left of these images, you can see a piece of Velcro and the corresponding geometry when touching this Velcro. Now, if we compare DIGIT to the leading tactile sensor commercially available at the time, this was the Biotech. Unfortunately, they've gone bankrupt since then, but both of these sensors are small enough that can be mounted on multi-finger robotic hand. But DIGIT has about 3 orders of magnitude higher resolution compared to Biotech, while being about 3 orders of magnitude cheaper for end user. And in addition, DIGIT is entirely open source. So if you want to build one, as long as you know how to cast silicon and 3D print objects and order online electronics, you can actually do this with a little bit of help. Now, DIGIT is by far not the best possible tactile sensor in the world. There are many limitations, and some of the limitations include sampling rate. Because we are using a camera as a transducer, we are limited by the sampling rate, which is typically slow for cameras. Digit has a resolution, temporal resolution, for example, of about 60 frames per second. Another limitation is the fact that because we use camera, we effectively generate large amount of data. And in the moment when we have, for example, a whole hand sensorized, we're going to generate potentially hundreds of megabytes of data. So how do we deal with such a high bandwidth? What can we do in order to reduce the bandwidth necessary to communicate? Another issue is the bulkiness. Due to the minimal focal distance of the cameras that we use, this sensor is relatively thick. So digit is about 2 centimeters of thickness. And this is, of course, not always desirable. In some cases, like in fingertip, this is not such a big issue. But in other applications, like if you think about skin, this might not be very suitable as a form factor. And finally, the fact that effectively, out of all of these modalities that we've discussed before in the human skin, digit is only able to capture these geometrical informations from which we can extract shear and normal forces. But nonetheless, we are not able to extract other informations like heat, vibration, and so on. So over the years, we've been studying we've built many different prototypes and studied different solutions in order to overcome these limitations. One of our early prototypes was OmniTac. This was a sensor designed to be omnidirectional, like a human thumb, with the idea that we would now use 5 miniaturized cameras for colonoscopies with a very small focal distance, so that we can then integrate multiple cameras in a single finger and look at how different form factors like omnidirectional is actually helpful. Another prototype that we built more recently is the EVTAC. The main advantage of the EVTAC is that we replace the normal cameras with an event-based camera. Now, event-based cameras are really interesting device because on one side, they can reach much higher resolution temporally. So with EVTAC, we're able to go up to 1 kilohertz of sampling rate. On the other side, because we are now going to only send information about changes in the pixels, we're also able to greatly decrease the amount of bandwidth necessary in order to transfer all of our data. Because we're not going to send the same pixels that are always still the same, but we're only going to send sort of a difference compared to the previous image. And we actually are not the first one to use event-based tactile sensors in the literature. Benjamin Ward-Sherrier had done this before us, but we were the first one to be able to leverage the modularity and the use of off-shell components by Digit, for example, in order to make this very simple sensor, very cheap, and quite reliable. And if we look at the type of data bandwidth that we can sort of have with event-based sensors, what we can see is that in comparison to a traditional sensor, a vision-based tactile sensor like Digit, an EVTEC only generate a peak data of which is about 12% of the number of bytes that we would need to transfer with Digit. And over the entire trajectory, this is only 1.7% of the data that a Digit would need to transfer. And this means that now suddenly, instead of saturating a USB 3 bus with, let's say, 5 fingers, we could in principle have hundreds of fingers or hundreds of sensors connected to the same bus, which is quite, from an engineering point of view, it's quite useful because we can now think of having full distributed sensors throughout the kinematic structure of a humanoid robot. Another sensor that we developed, which was also very interesting at the time, is the Digit Pinky here shown on the right. And the Digit Pinky was designed to be roughly the size of a human pinky, so it was only 1.5 centimeter in diameter. And the idea was that in order to achieve such a small size, what we would be doing was to decouple the electronics of the sensor from the actual sensing unit. So we would now introduce this concept of using fiber optics that would go onto this fingertip, and instead move all the illumination system and optical system, so the camera and the lenses, far away on the other extremity of the optic fibers. And this allowed us to really miniaturize down significantly the finger, and this proved very useful eventually in medical applications, where together with collaborator at Stanford, we were able to demonstrate that with the PNK and with the right machine learning models that we develop, we are able to detect which part of a prostate is actually cancer tissue and which part of the prostate is normal, sane tissue. And here at the bottom right, you can see some videos. And fundamentally, we are able to determine very well by processing the videos what is the stiffness of the material. And therefore, prostate tissue, which is sane, is a little bit less stiff than instead tissue, which is cancer, which is typically stiffer. Finally, the last prototype that we recently open source is the Digi360. The Digi360 is another omnidirectional sensor, but it also introduced several very interesting solutions. One solution is the fact that we are now including multimodal sensing. So I will show you in a second that compared to other vision-based tactile sensors, we are not only looking at the deformation of the sensor, but we will also be capturing other stream of data, for example, heat exchange, for example, vibrations, and we even have a smell sensor so that we can analyze the air and look what chemical compounds there are in the air. With the idea that maybe you look at something that might look like oil, and as a human, you are able to identify that this is oil, therefore will be more slippery. And with the sensor, with the sense of smell, we might also be able to disambiguate properties of what we are touching. And in total, Digi360 has 16 sensing modalities, including also IMU. And virtually anything that the human skin can sense, we are also able to sense it. In addition, another very interesting experiment that we did was to include a neural network accelerator directly inside the finger, with the idea that we want to be able to process locally the data, so that instead of having to transfer them to a computer, remote computer, we can instead locally decide which data are important, which data are not important, and only transfer the one that we consider essential. Now, if we look at the spatial and force resolution of Digi360, we took a lot of effort and care in making Digi360 the Rolls-Royce of vision-based tactile sensors, and the results is that Digit has a spatial resolution of about 7 micron and a force resolution of about 1.3 millinewton, which means that we are about 2 orders of magnitude or 100 times better than a human finger. In addition, here is the diagram of the multimodality that I mentioned before. And as an example, using Digi360, we're able to tap on a bottle, and by looking at the vibration, we are able to understand how much liquid there is inside the bottle just through vibration. As a humans, we would actually use a slightly different movement by shaking it and then looking at how the inertia matrix would change over time. Finally, with the use of on-device AI inside the finger, what we can do is that we can also replicate the human reflex arc that we have in humans, where if your fingers is touching something that is very hot, what will happen is that this message will basically travel to your backbone, and your backbone will decide will tell the muscles to start moving back before this signal has actually reached your brain. And with the idea of being able not only to process locally data, but also to do local decision making so that you can be faster in having this type of reflexes compared to having to transfer all the data all the way to the sort of centralized decision making system you have. Now, in the moment when we have hardware, the next step is to look into simulation, because hardware is great, but simulation is scientifically a very useful tool, because typically simulating can be faster, can be cheaper. And our small contribution towards simulation of touch was the open sourcing of a package called Tacto, where the idea was that we wanted to have a simulator which is not necessarily accurate in terms of physics, but we wanted it to be really, really fast, because if we want to be able to learn policies and control on top of sort of the simulator, we need to be able to have a simulator which is faster than real time. Otherwise, there is no point for, then it's faster to use real world data. And so when we started the development of Tacto, we made a few decisions with the idea that we wanted to have something that was able to do hundreds of frames per second. And it turns out that Tacto, in many cases, can actually reach a couple of hundreds of frames per second, which was pretty good at the time. And in particular, the main design choice that we made was to not rely on any single physics simulator engine, but instead being able to rely and piggyback on already existing physics engine. So, for example, Tacto could be connected with MuJoCo or Isaac Gym or PyBullet. It doesn't really matter. The only things that matter is that as soon as you're able to extract sort of meshes and force informations, you're then able to feed them into Tacto, and you're able to render basically how the tactile sensor would respond. And moreover, the definition of the sensor is parametric, so we can actually simulate multiple type of sensors. For example, here in this video on the bottom left, you have OmniTac, while on the bottom right, you have digit sensors. And in the moment when the simulator is actually calibrated to the specific sensor that you have, the simulation renderings are actually qualitatively pretty good. So here we can see on the top output from the simulator, and on the bottom instead the output from a real sensor. And qualitatively, they are pretty okay. Could be made better, probably, yes. But for us, the most important aspect was really this being fast, so that we can use learning on top of it. And in addition, the use of this simulator already can show promise in being able to do sim-to-real transfer. And so in our paper, we studied how using the simulator plus a very small amount of real-world data can result in much better performance for different types of models. In this particular case, we were trying to learn a model that identify what is the position and orientation of an object that we are touching. Now, after we have a hardware and after we have a simulator, the next question is, how do we process this data that we have? How do we make sense of all of this? And traditionally, for decades, people were manually trying to sort of process touch from first principle. But my personal opinion is very much that we should leverage AI for this type of role, and make sense due to the complex, rich nature of the data. And so over the last years, we've been trying to basically start the creation of this field of touch processing, where the idea is really to build this new computational field of science dedicated to understanding touch as a sensing modality. And this is a very new field, so obviously there is very limited literature existing out there. It's at the same time growing quite rapidly. But fundamentally, what I'm very interested in is asking questions along the lines of what are good features for touch? What are good representation of interactions? And how do we learn this representation? And also, what are the right structures and model in order to be able to process this type of data and representation? From the world of computer vision, we know that, for example, convolutional neural network are very good models because they incorporate the right inductive biases about spatial structure of the data. What would be the equivalent of a CNN instead for touch? And in touch, we don't only care about spatial structure, but we also care about temporal structure. So how do we incorporate the two in a way that is smart and makes sense? And I really believe that this will probably take several decades into the future to be able to solve this, or at least try to answer some of these questions. But at the same time, I think it's a very exciting place for the whole tactile sensing community to be in. And one of our small contribution toward this goal was in 2021, the open sourcing of PyTouch, which was the first machine learning library dedicated to touch processing, with the idea of trying to replicate a little bit the success of OpenCV, but for touch, where we wanted to be able to very easily connect sensors, to be able to very easily process sensor, and also have pre-trained models that you can just download from the internet and directly plug in and compare your own model very naturally, very easily. And using this library and other software over the years, we've been trying to explore the question of what type of representation do we need for touch. And two of the sort of hints that we already started to obtain over the year is this concept of being able to learn representation that can transfer across sensors. So if we now train with a number of different vision-based tactile sensor, and we then the features that we learn can already encode some information about touchiness, and this type of features would perform better compared to features learned from a single sensor. This is very, very interesting result. And also the fact that some of this representation that we can learn, for example, using self-supervised learning approach, can transfer across tasks, so that we don't need to specifically learn for a single task different representation, but we can learn something that is general enough that can then be used for multiple different tasks, downstream tasks that we might want to have. In this case, for example, detecting anomalies and doing vision-guided search and tactile servoing. We also looked more at the conjunction between learning representation in sort of during control. And one of our papers here was in collaboration with colleagues from Meta on this idea of trying to have a tactile SLAM system where throughout the manipulation, we are able at the same time to track what is the position of the object that we have in our finger, and also creating a 3D mesh of this object as we are rotating it. And this actually worked very nicely. So you can see at the end, at the bottom right, sort of the neural field that we obtained out of this object. Finally, the last sort of paper that I'll mention in this, from a processing point of view, is also looking at how do we provide semantic attributes for our raw tactile data. And in particular, how do we put together touch and language through the use of large language models, where we can now provide images from the sensor and basically ask the system to describe how would this feel like for a human. And this is also very interesting because traditional large language models are multimodal in the sense that they might incorporate language and vision, but they don't yet incorporate touch. So how do we incorporate touch also prominently there? Finally, over the years, we have also been looking at many different applications. Some of the applications that I've already hinted before include medical applications, not only for diagnosis, but also for prosthesis, where being able to give back the sense of touch to people that lost their limb, I think would be very valuable for our society. Metaverse, so being able to digitize touch and transfer touch over long distances and playing it back, this would of course be also quite interesting. From an emotional point of view, touch play a really important role, and it's great to be able to see your grandparent on the other side of the world and hear them, but if you are able to also physically feel them, it, I think, would have really a different value from an emotional point of view. E-commerce, where my dream is to have a tactile sensor one day where you can touch your favorite sweater and say, hey, Amazon, buy me a sweater that feels as soft as this particular material, or maybe that has the same thread as the sweater that I'm wearing. And finally, robotics, where most of our work eventually is aimed at. And specifically for robotics, I again want to point out the fact that compared to vision, many people in the community argue that vision is all you need. And if you have vision, you can solve all manipulation problems. But I think that this is a very short-sighted view of the world. And if you have ever tried to grasp an object with a real robot, you already know that vision is not going to be enough. This is a really hard task. The reason is because vision provides us only very weak cues about what's going on in the contact, especially in the moment when objects are rigid. It's very hard to distinguish if we actually are touching an object and if we are applying enough force, and even exactly where we are because of the occlusion of our robot and the hand. And on the other hand, on the other side, touch is a sense that has been, in some way developed for humans, exactly to provide us these two very valuable bit of information, which are what forces am I measuring, what is the vector of the force that I'm measuring, and also what is the position. And we know from several work, including the work of Andrea Del Prete, that knowing the position of the contacts is actually extremely important in order to be able to manipulate the environment. Because even very small changes between our estimate, small error between our estimate and the real position of the contact can sometimes result in catastrophic failures. And over the last decade, there has been an increasingly growing set of evidence that touch is actually important, and we are now starting to quantify this. One of the first works that tried to quantify this was a work that we did in 2018, where we wanted to learn a model that was capable of predicting the grasp stability. So in the moment when we are in touch with an object in our finger, we are basically going to predict, is this a good a good place to grasp, or should I move my fingers a little bit to increase the probability of having a good grasp? And in the moment when we have this type of model, we at the time trained it using self-supervised learning. So we had a robot spending about 2 weeks randomly trying to pick up a different object, and overall we collected more than 6,000 grasps from over 60 different everyday life objects. And in the moment when we then trained the model and applied it to previously unseen objects, what we noticed was that if we were only using vision for learning this system, we had a result of success rate of about 56%. But in the moment when we were using both vision and touch, we were able to increase this quite substantially up to 83%. And this was performance not on the training set, but on actual objects that were never seen before. And as you can see, the objects are relatively diverse in terms of shape, materials, weight, and whatnot. Recently, one of my PhD students extended this work to also include audio as a sensing modality, where very often when we grasp object, we obtain audio cue whether we are applying too much force. So you can imagine that, for example, if you have a rubber duck in your fingers and you're applying too much force, the rubber duck will squeak. And so what we did was that we improved the model from before by now considering a multi-finger hand and also including audio as an indicator of gentleness. And also in this case, what we saw is the fact that using vision plus touch compared to only using vision improved the performance of both for predicting the grass stability, but also for predicting gentleness. A work that we did with collaborators from TU Darmstadt was learning how to light matches, inspired from the work of Roland Johansson. And also here, it turns out that if we use imitation learning to copy policies from humans, if the imitation is done only using vision, we obtain a success rate of only 20%. But if we also include information from tactile sensors, we're able to increase performance up to 80%. Once again, highlighting the importance of tactile sensing, in this case for imitation learning. Finally, another work that also points in this direction is in the domain of in-hand rotation. So what we did here was that we learned using a sim-to-real approach. We learn how to rotate objects in simulation, and then we deploy the learn policy in the real world. And what we can see is, first of all, that the learn policy is able to generalize to many different objects that were never seen before during training time. This is actually a fairly stable policy. And we can also specify along which axis of rotation we want to be able to rotate the object. And this also works quite well. But the other aspect that is very interesting, once again, is that if we compare the performance of using prior perception, vision, and touch, these outperform using only prior perception and touch, and also outperform using only prior perception and vision. So it seems really that if we want to be able to reach 100% performance in manipulation task, using vision is great. It probably gives us 80% performance, but really in the moment when we want to fill this last gap, remaining gap, having touch is what makes these policies becoming closer to 100%, and it's also what gives robustness, simply because of the capability of touch, in my opinion, of generalizing better than just visual cues. Finally, even if you're doing teleoperation, touch play a really important role, because as an operator, being able to learn how to manipulate object in teleoperation is actually not so easy if you only use visual cues. But in the moment when you instead include also tactile sensing and you send the tactile informations back to the operator, this really helped the operator to learn how to do relatively complex tasks much faster with a much higher success rate. And in this particular work, we at the time used vibration to provide feedback to the operator. This was actually a horrible idea a posteriori, because it turns out that humans get used to vibrations. And so after about 1 minute, if your finger is constantly vibrating, you're basically your brain cancels this out. So To conclude, I would like to thank all my collaborators over the years. All of the works I've presented you today and others that I have not had the time to present you today would not be possible without their help. And I'm deeply grateful for having worked with all of these people and many more that I don't have the space to show you. And this is a lab picture with some of the people from my lab at the last one of the last barbecues we had together. And to conclude, what I have tried to sort of transfer to you today is the fact that touch is a very important sensor modalities, both in humans and robots, plays a really important role for fine manipulation. And touch sensing is a field that is really entering this type of digital revolution where we now have hardware which is as good or better than humans' skin. And the next frontier is this new field of touch processing where we want to be able to learn what type of representation and what type of models do we need in order to be able to process touch, to make sense of touch as a sensing modality. And overall, there is a growing evidence that touch sensing is going to be very important and even necessary if we want to have robots that are achieving the same level of performance than humans have in even simple tasks like grasping or rotating objects. And really, if we want to move from lab performance to real world performance, I am deeply convinced that touch is going to be the key sort of challenge to be able to achieve this. Thank you very much, and I'm very happy to take questions.